Have you ever stopped and wondered how we give instructions to a robot? Not just simple commands, but a perfect logical plan for a whole mission. Well, it gets right to the heart of modern AI and automation. And today, we're going to break down the absolutely brilliant logic behind it all. Okay, so let's start with a little thought experiment. Imagine you had to write a to-do list for something that never stops. Like your computer's operating system or a network server that's always on. How in the world do you give it commands that account for, well, forever? That one question right there reveals this huge challenge in computer science, and it perfectly sets the stage for a really clever solution. So let's dive into this forever problem. For the longest time, the go-to tool for this was a special kind of formal logic. And it was designed specifically for these systems that just run on, without end. That tool is called Linear Temporal Logic, or LTL for short. It's basically a super precise language for saying things like, eventually, this thing has to happen, or this critical error must never occur. You can see how it's incredibly powerful for describing the rules of a system that's supposed to run forever without a finish line. But, and this is a huge but, here's the catch. LTL is fantastic for describing what you want a never-ending task to do. But actually building a program that perfectly follows all those forever rules, a process called synthesis, is just incredibly mind-bendingly complex. It's kind of like having the perfect blueprint for a perpetual motion machine, but the actual physics of trying to build it are next to impossible. So if building for forever is just too hard, what's the alternative? Well, this brings us to the hero of our story today, a really simple but honestly profound shift in thinking. And here it is. Meet LTLF. That F stands for Finite Traces. This was introduced back in 2013, and it was tailor-made for a totally different kind of problem, tasks that have a clear finish line. So think about a rescue robot sent into a building. Its mission is to find an object and then come back out. That's a finite mission. It has a start and it has an end. This analogy really just nails the difference, doesn't it? The old way, LTL, is like trying to design an eternal engine that runs perfectly forever, a huge theoretical headache. But LTL fifth, that's like designing a specific one-time mission. It's focused, it's contained, and it has a clear definition of done. And that right there is the breakthrough. By simply shifting our focus from this infinite timeline to what's called a finite horizon, everything changes. We suddenly get these massive algorithmic advantages. Problems that were once way too complex become practical, they become solvable, and they become way more efficient. Okay, so this isn't just some abstract idea from a computer science textbook. The impact of this shift is very, very real. Let's take a look at how this logic actually makes its way into the world of AI and robotics that we see all around us. I mean, just look at this list. LTLS is now a critical tool in a huge range of fields. For AI, it's all about planning complex actions. For robotics, it's the key to motion planning. Getting a robot from A to B without crashing into anything. It's even being used in the business world to model and double-check workflows. This is a real practical powerhouse. And here's a perfect example of its power in action. In AI, the tools that are built from the ground up to use LTLF, what we call LTLF native tools, they just scale so much better. What that means is they can handle bigger, messier, more complex problems way more efficiently than the old methods that tried to force that forever logic onto tasks that actually have an end. Okay, so we know it's more efficient. We know it works. But how does it actually work? Let's pop the hood and take a simplified look at the pipeline for turning a simple LTLF instruction into a working program for a robot. So here's the simplified process. First, you define your goal using that LTLF language. Step 2, that logic gets translated into what's basically a giant decision-making map. The technical term is a finite automaton, but just think of it as a map of every single possible choice the robot could make. Then, step 3, a super powerful logic engine called a SAT solver searches that entire map to find one perfect path that guarantees success. And finally, that winning path is used to build the actual program that controls the robot. Now here's the really cool part. On paper, if you ask a computer scientist, the problem of finding that one correct path is still really, really hard. It's something called piece space complete. But, and this is the key, because we're dealing with a finite mission, the practical tools we have today, like those SAT solvers, are actually incredibly good at finding solutions for real-world problems. It's one of those amazing cases where the theory is hard, but in practice, it's totally manageable. But hang on, there is one last piece to this puzzle, and you could argue it's the most important one of all. See, it's not enough to just create a program for a robot. You have to be able to prove with 100% certainty that it's correct. So after our fancy system generates this brilliant plan for the robot, how do we actually double-check its work? This whole process is called model checking. And this is where designing for a finite mission pays off in a huge, huge way. And this slide reveals the biggest payoff of all. Just look at this. Trying to verify a system that we know will finish, one of our LTL systems, is piece space complete. Like we said, that's hard, but our computers can handle it. Now look at the alternative. Trying to verify a system that runs forever, the complexity just explodes. It jumps to something called X space complete. Let me put that in simpler terms. Checking the forever systems is exponentially harder. That's not just a little more difficult, that is a completely different universe of difficulty. We're talking about a difference so vast, it's almost unimaginable. So there's this massive incentive to create programs that we know for a fact will finish, because those are the only ones we can realistically afford to check for correctness. So when you put it all together, LTTF isn't just a clever little logic trick. It's really become a cornerstone technology. It's what allows us to design these incredibly complex, mission-focused AI and robotic systems that aren't just effective, but are also verifiable. We can actually prove that they do exactly what we told them to do. And all of this leaves us with a really fascinating final thought. By simply shifting our focus away from infinity and onto the finish line, we've unlocked this whole new generation of smart, reliable, and trustworthy systems. So the only question left is, what incredible, world-changing missions are we going to send them on next? Thanks for tuning in.